Hello, thank you for joining another video of thermodynamics. In this video, I'm going to talk about um, entropy balance. The entropy balance equation simply says uh, how entropy entered the system and how entropy is collected in the system and how entropy is leaving the system. So basically, we can write the balance equation by considering a system. Let's say you have a system at state one, and then during the process that the system uh, goes to state two. And if I take this entropy at state one is S1 and entropy at state two is S2, I can say that the total entropy change is equal to entropy uh, entered through the system minus entropy uh, left the system is some kind of entropy transfer, and there's entropy generation as well because of irreversibilities. Entropy generated in the system within the system, right? Entropy generated within the system. That this is the entropy balance equation in words. So this is not a conserved, entropy is not a conserved property. Why entropy can be generated or uh, entropy can be generated. So therefore, entropy is not a conserved property. Okay, so we can say that uh, this is actually delta S of the system entropy change, and then we can say this is S in minus S out, right? And plus Sj. Now we know that entropy generation is due to irreversibilities, is due to irreversibilities. And and what causes entropy transfer? How can entropy transfer in and out of the system? There are two mechanisms of entropy transfer. One is heat, and if you take entropy transfer by heat, you already know how to calculate the entropy transfer by heat. Entropy transfer by heat, S heat, is equal to Q over T. Q over T. Now T is the boundary temperature, and Q is the amount of heat transferred from that boundary, which is at T temperature. Now, for example, let's take a fairly large system like this, right? And here at the boundary, we have T1 temperature, and here at the boundary, we have T2 temperature, and here at the boundary, we have T3 temperature, and some other place we have Tk temperature. So across this boundary, some amount of heat Q1 is transferred, some amount of Q2 is transferred, and this is Q3 is transferred, right? And here it's we have Qk amount of heat is transferred. And likewise, we can have another places that transfer the heat in different amounts and at the boundaries kept at different temperatures. So if you want to calculate the total uh, entropy transfer by heat, during uh, the process, you can algebraically add these quantities together. So you have S heat total, right, can be written as summation Qk over Tk, right? This will give you the total entropy transfer due to heat or by heat, right? That's heat. And the other means of heat transfer is uh, mass. So if you have delta mass or S mass, right, or entropy transfer through mass is equal to mass times specific entropy at that location. Work does not transfer any entropy in and out of the system. Now, as I said, the entropy balance equation can be written as and total entropy entering S in minus S out, and entropy generation is equal to delta S of the system. Now, if we wanted to put the different methods of entropy transfer into this equation, entropy can come in form of heat and leave the system in form of heat. So the algebraic sum of that Qk over Tk, right, uh, is does represents both heat comes in and out. That and for mass, you can write plus uh, m dot ins, right? As also we can get, there may be several locations that mass can come into the system, right? If you say that the system has several inlets and outlets, right? Several inlets and outlets like this. So at each of these locations, we can see that m dot 1 s1, right? And you have m dot 2 s2, that's negative, and this is m dot 3 3s3, right? And you can have m dot k sk as well, right? Any any number of points. So we can add all the ins and out like this. Whatever comes in, we can represent by positive m dot in as in minus m dot out as out. This is for all the ins and all the outs, right? Plus S gen equals delta S of the system. Uh, Now we're gonna, uh, sorry, that should be, okay, just set out. Say M, whatever the mass comes in times entropy, right? You shouldn't put that rates in there. So, um, so bear in mind, these are specific entropies here. These are specific entropies. These are specific entropies here. But this is total entropy. By you multiply by mass, you get the total entropy. Now, if you have a closed system, when you have a closed system, in that case, there's no mass interaction. Therefore, we can take out this mass entropy in and out. So we can write Qk, Tk, right? That term plus S gen equals delta S. So if you have a closed system, this is simply the entropy balance equation. And if the system is adiabatic, then this term is gone, right? For adiabatic system, right? We have sigma qk tk equal to 0 because there's no heat transfer. So we have S gen equal delta S. So if the system is adiabatic, your change in entropy is just only S gen. That's what happening isolated system because isolated system is adiabatic and this is greater than or equal to 0, right? Always. So that's how we derive the increase of entropy principle. That's a side note. Uh, now let's see how do we modify this into control volume. Now, when it comes to control volume, we would like to consider rate equations. So in the rate equation, I can write the same entropy balance equation S in. So this is open systems. Can write same entropy balance equation S in minus S out plus S gen equals delta S. And yeah, heat interactions are there. So you can write, first of all, we take the rate form, take the rate. So we take the differentiate this equation uh, with respect to time. So I can write S dot in minus S dot out. This is time rate of change, time rate of entropy entering, and time rate of entropy generation. So rate of entropy generation. And this term, it's d, or we can say that ds over dt. I can write ds over dt. Now, assuming steady state. Now, steady state condition ds over dt equal to 0. So when it is equal to 0, we can say that s dot in minus s dot out plus s dot gen equals 0. Now, what are the ins and outs? We have sigma qk over tk, right? That's both represent both ins and out, plus m dot in, m dot ins, all the ins. I need to add all the ins here. So I'm going to add sigma ins, m dot in, s in minus sigma out, m dot out, s out plus s gen equals 0. Okay. Now, if you have single input and single output, single stream device, uh, single stream device, I can write for single stream device. Now, most of the devices that we're going to talk about in this course are single stream devices, but there are some multi stream devices as well. So we have sigma q dot k tk, right? And we can write m dot in. There's no sigma now because it's only one inlet and one outlet equals del plus, sorry, plus s gen equals 0, equals 0. Now we can say from mass balance or mass conservation, in the steady state case, m dot in is equal to m dot out, uh, that is equal to m dot. So I can write the same equation, this equation, q dot k tk plus m dot s in minus s out plus s gen equals 0. So these are specific entropies, okay? And these are specific entropies. And if the system is adiabatic, then what? Q dot k equals 0, right? Then I can write m dot s in minus s out plus s gen, s dot gen. There should be dot in here, s dot gen 0. Now we can write finally for a closed system, uh, s dot gen equals to m dot s out minus s in. The single stream device. And so that's all about the entropy balance. So what we started with is a general equation. Delta S of the system is equal to S in minus S out plus S gen, and then figured out how many methods that we have, how many methods that can transfer entropy in and out of the system. There are two methods. One is heat, the other one is mass. Then we can write the entropy balance equation, including those different types of entropy transfers, heat and mass. Then we can go ahead and reduce the equation to adiabatic closed system. And then we get the rate form of the equation for the open systems, and we can simplify that equation for single stream steady state device by using simple using the mass conservation also. We can reduce that equation to this, and going forward with that, we can say for adiabatic process that equation holds. Okay, thank you very much for watching this video. Hope to see you in the class.